Hello. The presentation today is an in-depth presentation of UV detectors. I guess that you have heard almost all of this at university, but it might be as it is for me. It was 30 years ago, and I don't remember everything, if any of what they tried to tell me. Hopefully, I compensate to what I have forgotten by learning things instead. This presentation is based on 30 years of experience of these detectors, and I hope that it will be useful in your daily work. The UV detector is the most common detector for HPLC. Could the reason be that this is ideal HPLC detector? It's a workhorse for detection and quantification of organic compounds. It's fast, accurate, and sensitive, quick and easy to set up, and requires only basic maintenance. However, to optimize performance and monitor critical functions, one needs to understand the basic physics of the absorption process and the working principles of the various instrument designs. This will lead to improved sensitivity, robustness, and better quantification. The first part is why we get the signal. This is a short version of the university lesson. I apologize if you already know all of this. Very simplified. The light from the lamp excites electrons in the sample to a higher state of energy. This makes the sample to absorb the light. Different molecules absorb light at different frequencies. The shorter wavelength, the higher the energy. Structures with double bonds often absorb UV light due to the presence of p electrons. Heteroatoms having non-bonding valence shell electron pairs also absorb UV light. Conjugated systems are particularly useful in spectroscopy. This is usually a series of single and double bonds. About 200 nanometers, excitation of electrons from the p, d, and p orbitals, and especially conjugated systems, produce informative spectra. This is a list of what wavelengths different bonds absorb. Unfortunately, it's not straightforward because most molecules contain several different bonds that absorb light in several different ways. This is one of the reasons you will get a spectra and not just a line. However, by using a spectra, you can identify which molecule you have detected, or at least get a very good ID. This is a conjugated system, a series of alternating single and double or triple bonds. Addition of one double bond increases the wavelength by around 30 nanometers because electrons are easier to excite. Have you ever wondered why acetonitrile is such a popular solvent for HPLC? The reason is that it absorbs light at a low wavelength and hopefully don't absorb at the same wavelength as the sample. You will not get any information out of your sample if the element absorbs all the light. Here's an example where the solvent is changed from acetone in water to acetone in hexane. This is also one of the reasons you can't buy a good library of UV spectras as you can do with GCMS. The UV spectra differ a lot depending on element. Everything influences spectra is not only the molecule itself, but also other things like solvent, polarity, pH, and temperature. In this example, it's the polarity of the solvent. Polar solvents give longer wavelengths. The excited state of most transitions are more polar than the ground state because of greater charge separation in the excited state. In polar solvents, the dipole-dipole interaction reduces the energy of the excited state more than the ground state. Hence, absorption in polar solvent with longer wavelengths. As you remember, light with longer wavelengths contains less energy. The reverse is also possible if the excited state reduces the degree of hydrogen bonding. Here the transition are N to P, and the shift of wavelength is due to the reduction of solvent hydrogen bonding. To make it even more complicated, the molar absorption constant also changes from solvent to solvent. A change in pH usually changes retention times. It might also affect absorbers. This can be very large if you are unlucky and the equilibrium shifts between two different forms. In this diagram, you can see really big differences when the pH is changed. The same sample is run at pH 2, 6, and 10. If you decide to use a buffer to control this, remember that they can also absorb the light. The example is a bit extreme. is anthocyanin, which changes between red, purple, or blue depending on pH. You can find it in food plants such as blueberry, raspberry, black rice, and black soybean. There are also temperature effects. Expansion of the solvent may be sufficient to change apparent absorbance and thereby the accuracy of the quantitative results. Temperature may affect expelia, which can be either chemical or physical, determination of nucleic acids, for example. For organic solvents, change in refractive index with temperature can be significant. Convection currents cause different temperatures to occur in different parts of the cell. The resulting Schlieren effect can change the apparent absorbance. Schlieren effect is what you see when you look at a candle and the background is sort of wavy. To control these problems, you should have as stable temperature as possible. Going through the basic university training, we are entering the technical part. To know how to handle a detector, you need to know how it works. There are two main detector designs: forward optics that are used for variable wavelength detectors and reversed optics that are used for diode array detectors. In the detector with forward optics, the light from the lamps first goes through a slit, then is divided into different wavelengths with the help of a grating or prism. Then a small portion of the light is diverted by mirror to be used as a reference, and the rest of the light hits the flow cell. In this case, we have a true reference that will be used to calculate how much of the light that was absorbed by the sample. In the detector with reversed optics, all of the light goes through the flow cell before it goes through the slit, and then it's divided by the prism or the grating. All frequencies are acquired at the same time by a diode array, and you will get a spectrum telling what frequencies of light that are absorbed by the sample, which is very nice and gives extra information. What you need to be careful with is the use of a reference. Because all of the light has gone through the sample, there's a risk that the reference wavelengths have been absorbed by the sample. Do not use very broad reference wavelengths, such as several hundreds of nanometers, and during method development, you must run samples both with and without reference to be sure that there's no problem. Actually, it's best to avoid the use of reference wavelengths when you have a diode array detector. These are examples of what you can use a diode array detector for. Peak current measurement, to see if you have the same spectra of the peak. If it changes between the start and the end of the peak, you have two different compounds co-eluting. Signal deconvolution. In this case, you acquire two or more wavelengths at the same time to get better signal to noise ratio and also less problems if the peaks are co-eluting, because you are using different wavelengths for different peaks. Spectra acquisition can also be used to help identify peaks. When you split up the light, you'll get something like a rainbow that sends the light to a diode array that measures the intensity of the different wavelengths. Have you noticed that when you look at a rainbow, there are actually one more rainbow with less light close to it? It's a second-order segmentation and also happens in a detector. Zero order is white light from a lamp with no segmentation. First order is segmentation of the white light into different spectra components. Second order is the same segmentation as in the first order, but on different places of the diode array, and it's less intense. As a consequence, the acquired data includes a selective wavelength, but also light of twice the selective wavelength, 3 times, 4 times, and so on. To control this problem, a second-order filter that is blocking the undecided extra wavelength is used. The problem with second-order segmentation is worse when the beam of zero-order light is broader. Now I'm going to talk about the different parts of the detector, and we'll start with the lamps. The deuterium lamp that is used for UV has a very high intensity when it's new, and it's also unstable, drift, and is noisy. The intensity significantly drops within the first 100 hours. Then the decrease is slow, steady, and the light is stable. The lamp typically loses about 50% of the intensity into 1,000 hours. It also loses about 6 hours every time you switch it off and on again. Sometimes it's better to leave it on if you run lots of samples every day. The But to get light in higher wavelengths, when UV lamp is not efficient, some detectors have a tungsten lamp. This lamp has a long lifetime, usually more than 10,000 hours. Light from both lamps are mixed together to get a broader range. When we look at the different intensities at the different wavelengths, it's not linear at all. To compensate for this, the detector has software that makes the intensity more or less even for the different wavelengths. Next thing to consider is the flow cell. The response is proportional to the concentration of the analyte in the flow cell. It's very important to map the flow cell volume to the application. Large cell volumes give good sensitivity but contribute to band broadening. Light entering the flow cell non-parallel to the cell walls will scatter and absorbs on the internal cell walls and reducing sensitivity. Can also happen due to change in refractive index in the gradient, temperature or pressure. Lowering the cell in the diameter leads to increases in the scattering effect. To get a good signal, the light path should be as long as possible. This means that the cell volume and the inner diameter of the measurement channel should be small. Half the inner diameter can give 4 times as high signal because then the light path will be longer within the same volume. Low volume and low inner diameter also lead to noise. To use this, get as much light as possible through the flow cell. 4 times light is the same as half the noise. To decide what cell to choose is difficult because we want a long, narrow cell for sensitivity, and this gives scattering effects. A narrow cell also makes it difficult to get enough light through it. The size of the flow cell depends on the peak volume, and the volume of the cell should not be more than 10% of peak volume. Peak volume is calculated as the flow times the baseline width of the peak. In the example on the left, the cell volume is okay, as only part of the peaks is in the cell at the same time. In the middle example, the volume of the cell is so high that 2 peaks can be in the cell at the same time. If this would be a real sample, you would only have seen 1 peak with a strange peak shape. In the third example, the smaller cell is used and the peaks are separated. This is what a flow cell looks like in a Thermo Scientific Ultimate 3000 detectors. Techniques be exchanged, and when you put in a new cell, it clicks into place. The cell type is automatically recognized by the detector. It might be a good idea to have a few cells with different volumes to choose from, depending on the application. There are 2 kinds of cells. The quartz cell, they are a piece of glass with a hole through them. They are robust and can withstand reasonably high back pressures. The other kind of cell is a LightPipe. This is an old Thermo patent that today is used by most manufacturers of UV detectors. The cell looks like a capillary from DC column, and they have some advantages and disadvantages. The use of total reflection between the thin silica walls and air outside the capillary. This gives a wider critical angle, more light transmission possible. Silica have also less problems with contaminations getting stuck on the cell walls. As always, there are also some disadvantages. They require optical fibers for light coupling and are much more difficult to manufacture. And the main problem is that they can't withstand as high back pressure as a quartz cell, and we don't recommend that you have switching valves after the cell, and be very careful with fraction connectors. This is what the LightPipe cell of the Thermo Scientific Vanquish diode array detector looks like. They come in 2 sizes, 60 mm long 30 microliter cell and a 10 mm long 2 microliter cell. To get maximum sensitivity, you should use the long cell, but be aware that the flow must be reasonably high, otherwise dispersion in the flow cell will be too much. With a flow of 0.00 milliliter a minute and upwards, it works very well. This chromatogram is a comparison of 2 detectors and 3 cells. Everything else is identical. More modern detectors, such as the Vanquish diode array, have better cells and electronics. Even with a smaller cell volume, the detector limit is lower than older detectors. Because of the deployment of the detectors, it is not that much difference in performance between a diode array detector and a variable wavelength detector. With earlier generations of detectors, the detection limits were much better for single wavelength detectors. This is a list of cells for the Ultimate 3000 and the Vanquish. It's in the presentation just as a reference. Next topic is a band and slit width. On a variable wavelength detector, the bandwidth is defined by the entrance slit. The optical resolution is defined by this, and you can't get better resolution than the slit width on any kind of optical detector. If you need better resolution, you must choose a more narrow slit. There are two versions of the Ultimate 3000 diode array detector. The RS, which have two settings, narrow and wide, and SD with a fixed slit. The Vanquish, you can set the slit at 4 different positions. This is a typical diode array detector. The light will first go through a slit that will define the optical resolution of the detector before entering the cell. After the cell, the light is divided into a spectrum and collected by diode array. They usually have 1024 diodes. Each of them get about 2 nanometers of the light, and the bandwidth is how many of these you bounce together. If you, as an example, have 4 nanometer slit, there is no use to have a bandwidth less than 4 nanometers. The resolution can't be better than the slit width anyway. When you decrease the slit width, the baseline noise and the spectral resolution will increase. If you increase the bandwidth, the signal-to-noise ratio will increase and the spectral resolution will decrease. With a slit width of 1 nanometer, we get peak spectra with high resolution but quite a lot of baseline noise. This setting is useful when you want to make spectral libraries. With a slit width of 60 nanometers, you don't get as much information about the peak spectrum, but much less baseline noise. This kind of setting is used when you want to quantify peaks and not necessarily need a spectrum for identification. Even if a monochromator is set to a single wavelength, the light emerging from the cell from exit slit would have a Gaussian distribution of wavelengths. The spectral bandwidth of this light is defined as the wavelength range at half height of the distribution. It is important to match the spectral bandwidth with the natural bandwidth in order to avoid deviations between observed absorbance and true absorbance. This is another example of how to set the bandwidth with the help of a spectrum. As shown in these examples, with low bandwidth, you get more noise but better spectral resolution. When the bandwidth is increased, the spectral resolution decreases, but you get better signal-to-noise values. The relation between light and noise is 4 times the light is half the noise. You need to figure out what is most important for you, as high spectral information as possible or the best signal-to-noise ratio. It's not possible to get both at the same time. Another problem is that linearity is affected by bandwidth. The linearity is excellent between 1 to 4 nanometers of bandwidth. From 8 to 100 nanometers, linearity permanently decreases. In a decided bandwidth, it might be a good idea to check the linearity by injecting different concentrations of the sample. It is the same with the slit width. A narrow slit always provides both a slightly better correlation coefficient and a slightly better linearity. We continue with some more settings. This time the data collection rate and time constant. First, it's a data acquisition rate. This is how many data points are collected in a second. Too few data points affects peak form, reduces stability, and area precision, as in the left picture. A minimum of 20, ideally 30 to 40 data points a peak is required. Unfortunately, as high data collection rate as possible is not good, because high data collection rate also increases the noise. Here is an example of the same sample run twice with different data collection rates. It's easy to decide what looks best. 25 times higher data collection rate is not the same as 25 times as good data. The other important parameter for data collection is a time constant. This parameter tells how quickly the detector responds to a change in the signal, and the definition is how long time it takes for a peak to go from 10% to 90% to its final value. Too small time constant gives a noisy baseline and too long distorted peaks. This is what can happen if you have completely wrong data collection rate and LightPipe. It's the same sample, element, an instrument. The area is the same. The peak shape is very different. The flat broad peak has 2.5 Hz as data collection rate and a response time of 2 seconds. In the blue chromatogram, the data collection rate is increased to 10 Hz and the response time lowered to half a second. There are really big differences in the peak shapes if you use the wrong settings. Well, you can't just make everything lower and make it better because noise is much more influenced by time constant than by data collection rate. To get a good chromatogram, you need to set this right. And this is by far the most common problem when a chromatogram looks noisy. Too low time constant make noisy chromatograms and too high distorted peaks. If you use Thermo Scientific Chameleon 7.2 CBS, the program wizard has a dedicated step for setting the correct data collection rate and time constant. If you use this, you will get better chromatography, and if you don't believe me, at least try it once. Reference wavelengths. This is another difficult topic because it can give both advantages and problems. Reference wavelengths work very well with a variable wavelength detector. This is because the light is diffracted before it enters the flow cell. This is not the case for a diode array detector. You can use any diode or bunch diodes as a reference. This might seem as a good and flexible solution. Unfortunately, all light has already been through the flow cell and might have been absorbed by the sample or the element. The selected reference and acquisition wavelengths are the same. The resulting signal will be 0. What you should do is select the reference wavelength in an area of the spectrum where there's as little absorbance as possible. And of course, the reference wavelength range should not interfere with the absorbance range of any compounds of interest. When it works with the reference, it can compensate for fluctuations in the lamp intensity, changes in absorbance, refractive index during gradient analysis, or background noise. This is an example of how to set the reference. Run the sample with the diode array detector and then try to find a quiet area of the spectrum as a reference. The compound is the same as in the example about how to set the bandwidth. This is what can happen when you use a reference wavelength with the diode array detector. You can get random noise, spikes, drifting baseline, or several other unwanted surprises like negative peaks. With this, I have some suggestions. First, always try to develop a method without the reference wavelength. Do not use a narrow bandwidth with high reference wavelength. If you experience intense noise in the UV detection, switch off the reference wavelength to see if the effect is caused by the reference wavelength. In case you observe effects caused by UV or visible lamp, replace the visible lamp or use wavelength where the visible lamp is not needed. If only the UV lamp is on, do not use high reference wavelength settings due to low intensity and high noise in this wavelength range. And most important, always run the sample with and without reference during the method development. Now we're getting close to the end of the presentation. There's only a few more challenges in UV detectors to discuss. Stray light is radiation emerging from the monochromator of all wavelengths other than the bandwidth at the selected wavelength. It arises from imperfections in the grating, optical surfaces, diffraction effects, as well as wide bandwidth and slit width settings. This is getting worse when the detector is getting old because of accumulated dirt and worn out mirrors in the detector. It always causes negative deviation from van der Waals law, which in this case is loss of sensitivity or linearity. This is how linearity is affected by stray light. Typically, an older detector cannot be used with as high absorbances as a new detector. You need to check this at least once a year to know the limitation of your detector. In example, the gradient is quickly changed from 0 to 10% of methanol in water. There's no sample. Everything is caused by refractive index changes in the flow cell. Elements have different refractive index, and the flow profile within the flow cell causes refractive index gradients. These gradients function like lenses and change the direction of the light, which partly hits the walls and is absorbed. The consequence is absorption similar to peaks. You can get negative peaks. Pump pulsation, particularly with high pressure gradient pumps, can increase the problem. To avoid this, detectors can be built with conical flow cells or have limitations for the light entering the flow cell. The easiest way to find out if you have these problems is to run a blank. This is the definition of noise. Usually 21-minute segments are measured and an average is calculated. What kind of problems can noise cause? Except for the obvious problem that high noise gives bad detection limits, it also causes linearity problems. There's noise coming from almost everything in the detector. Total noise arises from the variation in energy emitted by the light source, the optics in the detector, electronics, A to D converters, temperature variations, variations and jumps of the lamp intensity, absorbing gases in the optics, air fluctuations in the optics caused by temperature effects, refractive index variation of element in the flow cell, mechanical vibrations of optical components. The list is almost endless. It affects measurement of analytes with no absorbance because signal to noise is reduced. High absorption samples are affected because the linearity is affected. As you can see in the example, with increasing noise and stray light, you get problems with both low and high absorbing samples. You definitely need to do a performance qualification of the system now and then to know how it performs. This was all from a cold and very snowy Sweden, and I'm thankful for your attention. I hope that you have got a few interesting things out of the presentation and did not get too scared to use UV detector after hearing me talking about all the problems. As I said in the beginning, if you know how it works and the limitations, you will get much better results out of your instrument.